Let's talk about making free body diagrams in order to solve Newton's second law problems. So, first off, a few ground rules that we want to keep in mind as we're doing these. As you picture the object going in a circle, remember this about the forces. Any force that points towards the center, in other words, there's a centripetal force, we will label that as positive. Any force that points away from the center of the circle, we'll label that force as a negative force. And any force that points tangent to or perpendicular to the circle, we will ignore. So again, instead of right being positive and left being negative, or up being positive and down being negative, towards the center is positive and away from the center is negative, and you can ignore anything that's tangent. Here's another big thing to keep in mind when you do these. Never, never, never label centripetal force on a free body diagram. Centripetal force is not a type of force. It's telling you what some other type of force that we've already discussed is doing. So tension can be a centripetal force, or weight, or normal force, or friction, or gravity. Any of those can be the centripetal force, and those are the ones that get labeled on the free body diagram. So never put centripetal force on a free body diagram. Let's do a few examples here to sort of talk about how would we solve one of these. So let's imagine this. Let's say you've got a roller coaster car not attached to the track, good design, on the top of a loop. Or equivalently, you've got a ball on the top of a string. So you're swinging it around in a circle, and this is right here on the top. So once we've got our situation in mind, we want to draw a free body diagram. So I'll do it for the ball here in this case. We would have tension down towards the center of the circle, and weight or gravity down towards the center of the circle. Now for the car, I might call that tension normal instead, but it's the same thing. So once you've got that set up, you know how to set up your Newton's second law. Here's how you're always going to do it. The centripetal force is equal to mass times centripetal acceleration. So we start with Newton's second law. I really should have a sum right here in that case. So what are our forces? Well, according to our rules, these both point towards the center, so they're both positive forces. So tension plus the force of gravity is equal to mass times the centripetal acceleration, which is v squared over r. So this whole side becomes mv squared over r. From here, they might ask you to solve a bunch of different things. The most common is tension, but maybe they give you the tension's breaking point and ask you for the maximum velocity in that case before it snaps. Or they could ask you for the radius. They could ask for any of them, but tension is the most common. Another common thing that they do in a lot of these is to have a limiting situation. So let's say, what's the minimum speed before you fall out of the loop here? So in that case, right when we start to fall out of the loop, we would have no tension or no normal force in the case of the roller coaster. So this whole part would be gone, and we'd be just left with Fg. So Fg becomes mg when we plug in for it. This part's still mv squared over r. The masses cancel out, and we solve for this. The velocity is equal to the square root of the radius times gravity. This again is a minimum speed before we fall out of the loop there. Let's take a similar situation. Let's say you have a car on the bottom of a loop right here. Or, same thing, a ball on the bottom of the loop, and we're spinning in a circle like this. So, let's follow our rules, free body diagram. So the tension points up towards the center. Gravity, aka the weight, is down. So when we go to set up our Newton's second law equation, we have tension is positive up, minus the weight out of the circle down is equal to mv squared over r. And again, what they ask you to solve for from this point can vary a lot. Let's look at another example here. Let's say you've got a car on top of a hill. So it's on the outside of the loop this time. Let's do our free body diagram. In this case, we've got normal pointing up away from the center and weight down towards the center. So when we go to set up our Newton's second law equation, the weight gravity is positive minus the normal away from the center is equal to mv squared over r. Once again, a common thing that they might ask you for on this one is if you go too fast, the weight will not be big enough to give you a centripetal force to keep you in the circle, and you'll fly off. So what is that value? Well, right when you start to fly off, the normal force will be 0. So that will drop out. So you get mg is equal to mv squared over r. Hey, that's the same thing we just had. So this maximum speed is also the square root of rg. Again, though, in this case, it's a maximum speed before you fly off, not a minimum speed before you fall in there. Let's try another one. Here's my attempt to draw a car going around a circle here on a road. So it's sort of coming out at you this way and driving it around in a circle there. So from the car's point of view right here, we've got the normal force up, we've got the weight down. Both of those are tangent to the circle. What's actually pointing towards the center there? Something's got to be, it's friction in this case, that keeps the car from sliding out in a straight line in the circle. So when we go to set up Newton's second law, all we have, the only thing that counts is friction. So friction is mv squared over r. Substituting in for friction, that's mu times normal force is equal to mv squared over r. Now, if this is on a flat roadway, the normal force is equal to the weight, so that would be mg. And if you solve for v in that case, we can also get a maximum velocity. In this case, the maximum velocity is the square root of rg with a mu inside of it as well, because friction's got to be involved. So square root of rug in that case there. Let's look at another one, the gravitron. So on the gravitron ride, let's say you've got a ride that's spinning around and around and around like this. If you spin fast enough, an object will stick to the wall right there. So what's the free body diagram in this case? Well, we've got gravity down, the object presses into the wall, and therefore the wall presses back into it with the normal force. And it wants to slide down, but if it presses in hard enough, friction will actually keep it from sliding down there. So let's use this free body diagram to set up our Newton's second law. In this case, it's the normal force that points towards the center. So normal is mv squared over r. By the way, we can solve for the normal because we know friction equals mu times normal, so I'm going to do that, friction over mu. But also, we know the friction force has got to be equal to the weight because it's not falling down. So I'm going to substitute in for friction. Mg over mu is equal to mv squared over r. Notice, once again, just like in the problems before, the masses cancel out. And so you can find this minimum speed here. The minimum velocity is the square root of rg again, but this time we're dividing by mu. Any slower than that, and we won't press into the wall hard enough, and we'll slide down. We won't get enough friction there. Let's just do two more here in this case. In this one, let's say we've got a ball of small m attached to a string, and it goes down through a tube, and it's hanging next to a massive big M. If I spin it just right, this thing will remain balanced. Gravity pulling down on this one will balance the inertia of this one. So, so what is the force that's pulling this ball into a circle? It is strictly the tension. So tension points towards the center there. So when we set up Newton's second law, we can say tension here is equal to the weight of this big guy. Notice this isn't little mg, that would be the weight on him. It's big mg. So this thing's supplying the weight that's pulling this towards the center here. And that would be equal to mv squared over r. This situation actually could never perfectly happen. Sometimes they approximate it because gravity would be pulling down on this and it would cause it to dip just a little bit. So in reality, we would actually have something closer to this. Here is the ball and it is dipping down beneath the horizontal a little bit, some angle theta. So when I go to do my free body diagram for this one, I would have tension actually in the y right here, and that would be balancing gravity there. And tension in the x would be the one that's actually causing it to go in a circle. So when I write Newton's second law for this situation, it would be tension in the x is the centripetal force, mv squared over r.